Black holes are some of the most remarkable objects in the entire universe. They are regions in space and time where there is so much mass, so much energy, and so much matter collected in one tiny area of space that nothing, no matter how fast it moves, how much it accelerates, or even if it moves at the ultimate cosmic speed limit, the speed of light itself, can it get out. Once you cross the event horizon, it's impossible to escape. But what happens on the inside? Must you, as so many have said, inevitably and inexorably head towards a singularity? Or could there be another fate awaiting you? Find out on this edition of the Starts With a Bang podcast. There are three separate known ways that real physical black holes arise in our universe. The first is the most conventional of all. You get a massive star, one many times the mass of our sun, that reaches the end of its life. In its core, after fusing hydrogen into helium, it then fuses helium into carbon and goes even further. The incredible pressures from the outside and the amount of mass in the core allow it to contract, heat up, and fuse carbon into oxygen, oxygen into neon, sulfur, silicon, and eventually all the way up into creating iron, nickel, and cobalt in the core. Once you reach that point, there's nowhere further to go, and if your core is massive enough, it's simply going to contract until it reaches a runaway state, until it reaches a critical temperature and density where there's a runaway fusion reaction. The outer layers get blown off in a catastrophic supernova explosion, but the insides implode. If it's not quite massive enough, you'll make a neutron star, which is some version of a failed black hole. But if your core is massive enough, even the neutrons themselves will collapse. You'll create an event horizon, and everything will collapse down to what we know as a black hole. Alternatively, failed black holes, these neutron stars that we talked about, get a second chance. If they either accrue enough mass that they will collapse, or two neutron stars collide at their center, at their core, they can create a black hole. Once they cross a critical mass threshold, you can create an event horizon, and that causes the collapse of everything down past the event horizon, past where anything can see, past where light or anything else could get out. There's a second chance for supernovae that don't make a black hole to get there after all. And finally, there's the direct collapse method. When there's no way for a massive star, a massive cloud of gas, or any massive enough object to resist the force of gravity, it can go out not with an explosion or a cataclysmic eruption, but with a whimper. It can just simply gravitationally collapse past that critical point, create an event horizon, and again, you'll arrive at a black hole. From the outside perspective, from someone outside of the event horizon who is always outside the event horizon, what happens is fairly interesting. We see mass falling in, and once an event horizon is created, what you'll see for that infalling matter is it will appear to slow down and get redder and redder and redder in color, going into the infrared, microwave, and even radio portions of the spectrum, but it will only ever appear to asymptote towards the event horizon. The reason for this is gravitational relativistic effects, things like gravitational redshift, gravitational time dilation, and what happens is all of that infalling matter will appear to get spread out across the surface of the event horizon, across that surface area. From an outside perspective, no matter ever appears to fall in. But that isn't because it doesn't fall in, that's due to the properties of Einstein's relativity. It's very difficult to create a black hole. In order to make one, you have to overcome the conventional limits of matter. For example, when a star like the Sun reaches the end of its life, it will have fused hydrogen into helium and helium into carbon. But owing to the limits of matter, the fact that the Sun is only one solar mass, it can't go any further. As a result, it will gently blow off its outer layers, and the core of carbon and oxygen mostly will contract down to the limits of matter itself, creating a white dwarf. However, this white dwarf will be made up of atomic nuclei and electrons, and these electrons will exert a force on one another owing to the Pauli exclusion principle. There's a quantum rule that no two fermions, and electrons are examples of fermions, can occupy the same quantum state in the same physical location. This is how something as massive as the Sun will remain stable even when its mass is compressed into the volume of Earth, even when it's hundreds of thousands of times as dense. The electromagnetic force, owing to the quantum effect of the Pauli exclusion principle, will keep this matter from collapsing down any further. If you overcome that, for example, with a neutron star, well, neutrons also behave as fermions, and they also obey the Pauli exclusion principle, only with neutrons and the nuclear force, the strong nuclear force, instead of electrons and the electromagnetic force. It's like an enormous atomic nucleus, incredibly dense, where something the mass of the Sun can be compressed into a physical size, maybe only 10, 15 miles or around 20 kilometers across. It's so incredibly dense, but still it can hold itself up. In fact, there's an even further state where the neutrons themselves will be destroyed, but the individual quarks and gluons that make them up, the quarks themselves are fermions, have this theoretical, even denser story, but still they obey the Pauli exclusion rule, and no two quarks with the same quantum properties can occupy the same quantum state. There are limits to what matter is allowed to do and how dense it's allowed to get, and as long as you don't cross that critical threshold necessary to make a black hole and obtain an event horizon, you will just have these degenerate states of matter. In all of these cases, there are forces resisting one another. The gravitational force is always pulling inward. It's always working to pull everything in, to contract everything, to collapse everything down. But in each of these cases, there are forces resisting it. The quantum laws of nature, via either the electromagnetic force in the case of a white dwarf or the nuclear forces in the case of a neutron or a quark star, will hold it up against gravitational collapse. But there's a limit to how strong and how effective those outward pushing forces can be. The reason is that there's a limit to how fast these forces can travel and how strong they can be. All of these forces can only exert an outward push at a quantum level based on the probability of a virtual particle like a gluon or a photon traveling outward. There's a threshold to make that probability more or less likely, and that threshold, that speed threshold, is the speed of light. An interior particle, in order to exert an outward push, needs to transmit a force-carrying particle further away from the interior gravitational source. But how can you do that? How can you, from further down inside the black hole, exert a force outward when you know that to reach outward, to reach away from the center of gravity of a black hole, in order to make it to the event horizon, you would have to travel faster than the speed of light, something that no force can do. even from across the universe. The gravitational force, the electromagnetic force, the nuclear force, they are limited by the speed of light. Nothing can go faster than that. So how then do you propose to overcome the gravitational force, pulling matter inward by exerting an outward force that's limited by the speed of light? This is extremely difficult. In fact, according to the current laws of physics, it's not physically possible. If you're outside the black hole, like we said earlier, you'll only see when masses fall in, they asymptote to the event horizon, and that's because there's a relativistic effect occurring there. But from the point of view of an object falling in, there's no change. If you freely fell into a black hole, once you cross the event horizon, you would notice some visual changes in the outside world, but you wouldn't notice any physical changes, unless, that is, you turned on your rockets and you fired them as hard as you could to try and get out. What you'd find is that as soon as you did that, as soon as you fired your rockets and you looked, how could I get out? You would find a tremendous problem. You would find the center of gravity of the black hole exists in all directions. There's no direction you can move in or accelerate in that would take you farther away from a singularity if you were falling in from rest. And the reason for this is that there's no trajectory that will take you out. There's no path you can take moving at the speed of light or below that will take you away from the center of the black hole. This is the first reason why we think a singularity has to exist, because once you cross that event horizon, any direction you attempt to go in will take you to the central mass, whatever it is, at the center of a black hole. Okay, you ask, but what if it isn't a singularity? What if there's some type of really dense, ultra-degenerate matter that somehow can hold itself up? Well, here's why physically that can't happen. There can be finite forces exerted from inside a black hole. For example, all of the particles falling in will have their gravitational effects still there. However, no matter what that finite force is, no matter what that outward force is, if you are inside the event horizon, that force can never be sufficient to overcome the gravitational force that pulls you towards the central singularity. The only way to keep yourself from hitting whatever exists at the black hole center would be to travel faster than the speed of light. Not only can none of the matter or energy in the universe that's known travel faster than the speed of light, but none of the known forces of nature are capable of propagating faster than light. Any particle that falls past a black hole's event horizon is going to be destined to be destroyed, to be torn apart into its fundamental constituent particles. And those particles have no way of feeling an outward force that pushes them away from the central singularity. There's no way to experience an outward net force in comparison to gravity once you've crossed the event horizon. Any particle that falls past a black hole's event horizon is destined to come to the singularity, whatever form that takes. And it takes on different forms. If you have a black hole that's made solely of mass and isn't rotating, that singularity will be a point. In a Schwarzschild black hole, the singularity is a single point of infinite density. If your black hole is rotating, that singularity takes on a different shape. It gets stretched out in one dimension, meaning instead of a point, it's going to appear as a one-dimensional circle, as a ring, where the central singularity isn't a point, but is rather this ring-like entity. And no matter what direction you fall in from and what your trajectory is, you will inexorably wind up hitting one point along that ring. What a singularity is, physically is representative of the limits of our knowledge in both general relativity and quantum theory. It's something that all of the matter and energy contained within the black hole is stretched into a zero or one-dimensional singularity, whose extent is, if it's anything at all, is smaller than the Planck length, is smaller than about 10 to the minus 33 meters. This doesn't mean at some level, if we come up with, formulate, and understand a quantum theory of gravity, that there won't be some additional new physics that goes beyond what general relativity tells us. It doesn't necessarily mean on scales smaller than the Planck scale, we won't have some form of matter that obeys different rules than what we know. Or if quantum gravity effects become important before you reach the Planck scale, perhaps there is some degenerate form of matter that may be only extremely close to the Planck scale that does survive. Because what a singularity is it's the limits of our current knowledge in a universe governed by general relativity and quantum field theory for the other forces. Yet, no matter what you are or what state you were in when you crossed the event horizon, if the universe had enough mass in one small, dense location to create a black hole, you're inevitably destined to arrive at its central singularity. There is a singularity there, as the laws of general relativity and quantum physics make its existence unavoidable. When we have a true, complete theory of quantum gravity, we'll know for certain what's contained at that point. But until then, all we know is that the laws governing particles, matter, energy, as well as space and time, they all break down. Unless a new law of physics comes along, there's simply no way out of that conclusion that at the center of a black hole lies a singularity. The Starts With a Bang podcast is only made possible through the generous donation of our Patreon supporters. I'd like to thank everyone supporting us at the $5 a month level and above over at patreon.com/startswithabang. Thanks go out to Samir Kumar, Robert J. Hansen, Bakhtiar, Chris Shaw, Thomas Sola, Denier, Pedro Texera, Igor Mitrofanov, Jose Enrique, Frederick Martello, Sean Foley, Elver Sena-Sosa, Flo, Richard Jousey, DGE, John Kozura, Marcelo Barnaba, Nick Tomlinson, Rafal Wojciech, Danny, Alexander Marius, Gaijin, Andrew Douglas, Chris Hilly, Weller Tractor Salvage, Kelly Kudrick, Richard Swartz, Darren Redfern, Mark, Nick Delroy, Ranan Yechazel, Ron Lyle, Frank, Pavel Zazulski, Fraser Kane, Steve Shaber, Naked Bunny with a Whip, Jason Basanseni, Peter Williams, Mark Armstrong, Kevin Barnes, Patrick Dennis, Radek Nesbita, James Nance, Joe McFarlane, Amira Sosnick, Sidney Atwood, Harry Plumley, John Mithot, Nathan Hanna, Tomas All, Glenn McDavid, Benjamin Turner, David Taschioni, Philip Radulovic, John Seal, Braxton Thomason, Karen Garrison, and Zarko Opachik. Thanks everyone for tuning in, and I'll see you next time here for more Starts With a Bang.